Hi, hello everyone. This is Dr. Chiranjeevi Manike, Professor and Head of Data Science and Cybersecurity Department, MLR Institute of Technology, Hyderabad. As part of data mining video lecture series, in the previous lecture, I explained the basic concepts related to the Bayesian belief network, and now I'm going to discuss how the Bayesian belief networks would be trained so that we can apply these trained models to the classification. So here we are going to discuss how this Bayesian belief networks would be trained here. There are many scenarios possible, that is to train the Bayesian belief networks. Mainly the network topology or the layout of nodes may be constructed by the human experts or inferred from the data. So the network variables may be observable or hidden in some of the training tuples. So the hidden data case is also referred as a missing values or incomplete data in the case of a Bayesian belief network training. So several algorithms exist for learning the network topology from training data given observable variables. So the problem is one of the discrete optimization. So human experts usually have a good grasp of the directed conditional independencies that hold in the domain under analysis, which helps in network design. So experts must specify conditional probabilities for the nodes, like as we discussed in the previous lecture, the definition. We could define this Bayesian belief network, that is the combination of two components, that is a directed acyclic graph and conditional probability tables. So here these probabilities, whatever there we calculate in this conditional probability tables, these probabilities can then be used to compute the remaining probability values. So if the network topology is known and the variables are observable, then training the network is a straightforward. That means whatever the variables in the data set are observable and the topology is known, so then we can directly straight away we can train the network. It consists of computing mainly the CPT entries, conditional probability table entries, and as similarly done when computing the probabilities involved in the Navy Bayesian classification. This CPT entries would be calculated like how we done in this Navy Bayes classification. So when the network topology is given and some of the variables are hidden, that is the two cases we can consider, we can divide into this one. The first one is when the network topology is known and the variables are observable, then the training is a straightforward approach. But whereas the another case, when the network topology is given and some of the variables are hidden, that means some of the variables, like suppose if you take a data tuple and that would be described by set of variables like a1, a2 and so on, an. So a few variables are hidden and the network topology is given. In that case, the various methods to choose, that is from training the belief networks. So let us see in detail. So let us define what is a training set that will be given to this Bayesian belief network. Let D be a training set of data tuples like x1, x2 and so on. The size of the data set, that is number of samples. So training the belief network means we must learn the values of the CPT entries, that is conditional probability table entries. So let us take Wijk. It is a value in the conditional probability table. Conditional probability, the table for the parent variable yi and its values y small yij and its children's ui and with the values uik. So then this would be expressed as, that is entry in the conditional probability table would be expressed as Wijk equal to the conditional probability, like probability of yi equal to yij given ui equal to uik. We'll see example now. So let us consider the one conditional probability table for a variable lung cancer from that example. So in this case, if you take the value like Wij here, that represents 0.8. So here that would be represented in the form of like the probability I would express in terms of conditional probability, like probability of lung cancer, or I would write a short name LC equal to yes. That means patient having the lung cancer given the family history. So here this would be expressed how we are going to calculate this value Wij from this conditional probability table. So let me write the equation for that conditional probability. So probability of lung cancer LC equal to yes given the family history, that is a short name FH equal to yes having family history, and the smoker yes. So that is equal to 0.8 in this from this table. This table 0.8 represents the probability of having lung cancer given having a family history and also smoker. And similarly, you can also represent, like you can take another value, like suppose 0.5 in this conditional probability table of variable lung cancer. So here that would be represented in the form of conditional. So probability of lung cancer equal to yes given the family history yes, and smoker no. So that is equal to 0.5. So similarly, you can also take another, like suppose 0.9 in this conditional probability table. This would be expressed as like probability of lung cancer no given family history no and smoker no. So that is equal to 0.9. So this is the way we can calculate the values of any conditional probability table. So like for each this, if you go back to the diagram, that is sorry, there's no diagram here. Yeah. So that whatever the diagram we discussed, like directed acyclic graph with a set of nodes like lung cancer, family history, smoker, etc. So for each variable, like suppose there are 6 variables in that data set, 6 variables. So for each variable, and we would take the values and the respective, like suppose having a lung cancer and its parents or the family history and the smoker. So for each random variable, we have to calculate this conditional probability tables. So the weights are initialized to the random probability values. Next, gradient descent strategy, that is to perform the greedy hill climbing, will be used. At each iteration, the weights are updated and will eventually converge to the local optimum solution. So this is the way we train the model. Let us see how the gradient descent strategy works. The gradient descent strategy mainly used to search for the Wij value, that is the entry in a conditional probability table that best model the data based on the assumptions that each possible setting of Wij is equally likely. So in search for a solution along the negative of the gradient, that is the steepest descent of a criterion function. So we want to find the set of weights W that maximizes this function. So to start with, let us the weights are initialized to the random probability variables. The gradient descent method performs greedy hill climbing, in that at each iteration or the step along the way, the algorithm moves towards what appears to be the best solution at the moment without backtracking. So the weights are updated at each iteration. Eventually, they converge to the local optimum solution. So here, this is the objective function of this gradient descent, and this need to be maximized. So this can be done by following the gradient of in PS of W, which makes the problem simpler. So given the network topology and initialized Wij, the algorithm proceeds as follows. The first one is we have to compute the gradients for each ijk. That is, as I said just now, we have to calculate the conditional probability values for each variable in the network. So by using this equation, so once we calculate this conditional probability values for each random variable in the network, then we plug those values into this equation so that we can compute the gradients. Second step is take a small step in the direction of the gradient. The weights are updated. How the weights are being updated? By using this equation here. Here L is stands for the learning rate. Learning rate. Next one is renormalize the weights. This is the last step in this. So renormalizing the weights, that is, the weights should follow, that is in the range 0.0 to 1.0. So because as I said many times, like suppose if you take one value, let us say age, mostly we represent using the 3 digits, like suppose 100 years. If a person lives 100 years, then maximum we'll use the 3-digit number, else a 2-digit number. Okay, so suppose some 60, 70, 80, 88, 92, like this. And similarly, if you take another attribute called as a salary, and like suppose 2 lakhs, 2 lakhs or even 20,000 also makes sense. So 1 lakh, like there are numbers. So if you plot the distribution among these two attributes, and this attribute is going to dominate this value. So to avoid this, so this data need to be normalized, and each value, like suppose even the age or the salaries or any other attribute values, will be converted into the range that is in between the 0.0 and the 1.0. So algorithms that follow this learning, that is from called as adaptive probabilistic networks. So belief networks are computationally intensive because belief networks provide explicit representation of causal structures. A human expert can provide a prior knowledge to the training process in the form of network topology or conditional probability values. So this can significantly improve the learning rate.